All right, so let's look at the Otto cycle. This Otto cycle is really famous because it was discovered by a scientist called Otto, and with this name, there are many vehicles and many systems, especially vehicles like cars or trucks, that are designs based on the Otto cycles or the engines that works on the principle of Otto cycles. So let's look at how the Otto cycle works. So if we know the PV diagram for Otto cycle, let's say we have this is pressure and this is volume. Let's say on the right hand side, let's make TS diagram for the Otto cycle. So this is T, SS stands for entropy, as you know that. So we have for the Otto cycle, the easier way to remember is just make a line like this, draw a straight line, right, and then make another straight line slightly below that, and then just make join these two ends. I'm gonna explain later what these processes means, but as a matter of fact that we want to make it more easier to understand. And for TV diagram, let's make it something like this line. All right, so I know I can explain why it looks like this line later on, but for now, as a matter of fact, that I want to little bit use a little bit trick. So let's say our system is going in this cycle. So we name this as a stage 1, stage 2, stage 3, and this is stage 4. Similarly, in this case, this starts from stage 1, this is 2, this is 3, and this is 4. So from 1 to 2 it goes this direction, and 2 to 3 it goes to this direction, and 3 to 4 it goes down, and then 4 to 1 it goes this way. All right, so we can, as you can see from here, that at this particular coordinator, this particular position, and this particular position, this volume, this is a volume axis. So this volume and whatever falls in these lines are same, meaning that V1 equals V4, and here V2 equals V3. Similarly, here S1 equals S2 because this is S axis, and this is S3 equals S4. So what we are particularly interested in knowing is that from process 1 to 2, from 1 to 2 there is, if you see here, the volume increases as you go along positive v-axis, meaning that if you go in the reverse direction, the volume is decreased, thereby increasing the pressure. If you see these two label, you see the pressure is increased as you go along this path. So we see that from position 1 to 2, volume is decreased, but pressure is increased, right? So in thermodynamic terms, we can call this as isentropic compression. So if we see from position 2 to 3, we see that the volume remains same. If you see here, the volume remains same, V2 equals V3, but the pressure is going up. Pressure here is lower than the pressure in the third stage, meaning that as you go from stage 2 to stage 3, the pressure is increasing. So what happens, pressure is going up, meaning increasing, while volume is constant. So in thermodynamic term, we call this as constant volume heat addition. heat addition. The reason why we call this is a heat addition, because during this cycle in the engine, in the Otto cycle, the heat is added in the system this cycle. So we can also write this as Q in. Okay, so let's move on to position from 3 to 4. See that this is almost similar like the process from 1 to 2, but in this case the process is reversed, meaning that in the first case the volume was decreased, as a result of which pressure was increased in the pressure. But from position 3 to 4, the volume is increased but the pressure is decreased, meaning that the piston should have been expanded. So we can say volume is increased while pressure is decreased because it expands. And if you see here, the pressure in this position is higher than pressure in this position, so pressure is decreased. So from 4 to 1, this is also same as process 2 through 3. This is volume constant while volume constant, but heat is rejected. So this is constant volume heat rejection. So if we go to TS diagram, this is temperature and enthalpy. So in TS diagram we see from position 1 to 2, temperature is increased. So from position 1 to 2, temperature goes up, but entropy is constant. But we can call this situation in thermodynamics as isentropic heat isentropic compression. Right, so let's go to 2 to 3. The entropy increases and temperature increases. Right, temperature also increases, but this is same as process in 2 to 3. This is called constant volume, same as this constant volume heat addition. Constant volume heat addition. Again, 3 to 4. This is 3 to 4. If you see here, the enthalpy, now the entropy remains constant, meaning that S remains constant, but temperature decreases. And from 4 to 1, the S decreases. 4 to 1, temperature S decreases and temperature, but this is same as process in volume constant and heat rejection, meaning that temperature decreases somehow a little bit. So this is also same as process in volume constant and heat rejection. So these processes are same, but we are looking for different parameters happening in these situations.